So in this lecture, I shall need some basic notions, for instance, the notion of groups. But John Thompson, who spoke before me, did not define them, but you have all heard his lecture, so you know what groups are. Another notion is that of Lie groups. You don't know that, but you know what is Lie, and Lie is here all around. So if you are here, you know what a Lie group. And don't know yet what buildings are, but I shall tell you in a moment. So that's my subject. I have to talk about simple Lie groups. Groups have been classified long ago by Killing and Cartan. And the simple Lie groups, some of them you know very well, for instance, the linear group, SLN, the orthogonal group, the symplectic group, and then there are also some exceptional Lie groups, and these are really the object So shall I start again? Well, anyway, so far I didn't say anything very important, so it will probably continue that way. So there exist the simple Lie groups have been classified by, or at least Lie groups. Perhaps I say in a couple of words, a group plus another structure, namely the structure of variety. A Lie group is a group plus a structure of variety, and this variety is usually, well, for specialists in Lie groups, this variety is so-called analytic variety. But in the groups I am interested in, there are algebraic varieties. And an algebraic variety is defined over a field. So there is, in whatever I do, there is always a base field of the variety in question. And the algebraic groups are the groups which are algebraic varieties, and they have a definition field, and that is what will happen here. As I said, the Lie groups have been classified. The most common thing is the case of groups over the complex numbers, and there is a very remarkable result of Chevalet that says that essentially, if you are interested in Lie groups, in algebraic groups over an algebraically closed field, the classification is exactly the same for all base fields, including the complex. So if you know the classification of complex Lie groups, you know essentially the classification of Lie groups over algebraically closed field. And I want to remind you of this classification. Complex Lie groups, they are the so-called classical groups, and these are the groups that are very common, that you meet every day on the streetcars and so on, is the linear group, the orthogonal group, the symplectic groups, and then there are the so-called exceptional groups. And there are 5 exceptional groups. They have a name. Write that. There is a group G2, F4, E6, E7, and E8. These are my personal friends, and I shall talk later particular about E8. And don't ask me what is E8. I know it only via a certain picture called the Dinkin diagram of the corresponding group. And so I shall draw the Dinkin diagrams of those exceptional groups. Well, this one I shall not draw because it's too complicated. This one I shall not draw because it's too complicated. But E6 I shall draw. The trouble is that for me, everything is complicated. So this is E6. My God. This is E7, and this is E8. These are the diagrams of the group E6, E7, and E8. And so I am a specialist in exceptional Lie groups, and the only thing I know about them is these pictures. And I must tell you how from that one can get a closer picture of what they are. What I have done, what I have lived on, and I did have my life. I ate on these things. Are these diagrams, and I want to explain to you how from these diagrams one get a notion of what these objects are. And I do that by means of a geometric notion which is called the building. Now perhaps I tell you where the notion, the word of building comes from. I have worked on this object, and I had to introduce a terminology. And in this I had a terminology. The buildings are certain simplicial complexes, and the buildings are not any simplicial complex. They are very specific simplicial complex. For instance, there exist buildings of type E6, E7, E8, and these buildings, in these buildings, there are sub-complexes which I used to call skeletons. And then Bourbaki talked about these things in his book on Lie groups, and they did not want this terminology of skeletons because it was a little bit too macabre, and they found a very consistent terminology where we had buildings. Well, in fact, we had, first of all, construction is the opposite of what would be the construction in life. First of all, the basic object in these things are the so-called vial chamber. Vial chamber is a notion that was, well, named in that way by Bourbaki. It's because they are used in Weil's theory of simple Lie groups. The Weil chamber is a certain a given simplicial complex attached to the group, and so Weil chambers are simplicial objects. And this notion that I have introduced led me to build something out of Weil chambers. You take several Weil chambers and you put them together in a certain way, and that gives you the building. Perhaps I give an example. SL2 in the case of SL2, the Weil chamber is just a stroke. Well, actually, as I said, Weil chambers must be put to make a group. Weil chambers must be brought together. And for instance, for SL2, if you consider SL2 over, for instance, a field of 2 elements, the Weil chamber in that case will be a stroke, but then you must put several strokes together, and I prefer not to start drawing because for 2 reasons it's too complicated and I shall certainly make mistakes. So the building of SL2 is made of strokes. If I take SL2 over the field of 4 elements, of 3 elements, the Weil chamber in that case are triangles. And then you must put several triangles together and in a certain way, in a ramified way, which I cannot really draw. It's too complicated. But you must imagine these triangles put together and with some ramifications. For instance, here is a piece of the drawing, the case of SL2. Whatever. Anyway, the building of a simple group over a finite field, for instance, the building is a simplicial complex, which is already quite complicated. It's well, for instance, here would be a simplicial complex. And I can continue ad infinitum. And that would be the building of an infinite dimensional group, actually. If I want to have the building of SL2, it will be This is the building of the simplest possible group of type SL2 over, it's not even over a field, it's over the field of one element. That looks like this. But then if you want to construct the building over bigger fields, you take many copies of these things, of this tetrahedral. You take many copies and you glue them together in a certain specific way, and in that way you get building over, in fact, any field. If you take a big number of them, and if you glue them in the correct way together. Anyway, I had the problem of constructing the group E8. If I want to construct the group E8, as I told you, the only thing I know is this Dirichlet diagram. And this Dirichlet diagram tells me how to piece up the chambers. In that case, the chambers are simply simplicial complexes of a certain dimension, and if I want to construct a group of type E8, for instance, I must take, well, a big number of simplicial complexes, and I must glue them together. And there is a rule about how to fit them together to define E8. And in my early work, what I did was to describe these groups by means of a certain algorithm. And the algorithm was this. If I want to construct the picture corresponding to, say, to a group of type E8, this picture has different types of. When you have a simplicial complex, you have faces of dimensions 1, of dimension 2, 3, and so on, and there may be several types of faces of dimension 1. In fact, in the group of type E8, there are 8 types of vertices, and all these vertices are linked together, and you have the vertices of type 1. Let me number these: 1, 2, 3, 4, 5, 6, 7, 8. And if I take a building of type E8, it's a big object which has several vertices, some of type 1, some of type 2, some of type 3, and so on. And then the rule to construct the building is this. If you take one vertex of type 1, you consider all the vertices that are linked with that one. And this gives you a sort of local view of the building. Everything that is linked with one vertex of type 1. It's a local description of this object. And the rule that I discovered in my early work was the very following simple rule. If you take a vertex of type 1, and if you take all the vertices that are related to that one, you get a building of a smaller type, and you get the type in question by just removing from this picture the point 1. See, if I take this picture, and if I remove the vertex of type 1 on this picture, I get still something that is something that people who know will recognize. It's a picture of type D7. D7 is there are 7 vertices, and this is type D7, and the basic rule of the whole game is this. If you take a building of type, in this case of type E6, of type E8, if you take one vertex of type 1, and if you take everything that is linked to that type, it's still a building, but of smaller type, and in fact it will be a building of type D7 in this case. Buildings of type D7 are well understood. They are Let me try to describe a building of type D7 with the hands. You take in a seven-dimensional vector space a quadratic form, split quadratic form. You consider all the totally isotropic subspaces of the quadratic form. We have and these totally isotropic subspaces have certain dimensions. You have those of dimension 1, those of dimension 2, dimension 3, and so forth. But you take those of dimension 1, and you represent them by points. Those of dimension 2, you also represent them by points, and all these points are connected together because you have this big picture in a seven-dimensional space. You have this quadratic form, you have one-dimensional varieties, and these one-dimensional varieties, we have also two-dimensional varieties, and they are related together. And I'm sort of getting out of So let me try again. a building of type E8 is a simplicial complex in which the simplices are of dimension 8. And these simplices, called the faces of the complex, are glued together in a complicated way. But if you take, for instance, one face of type 1, if you take all the faces that are connected with that one, you get a simplicial complex of a simpler type, which will be of, and all these simplices form together a complex, a building of type 7. The building of type D7, I can give you a direct description of a building of type D7. I take in a 7-dimensional space quadratic form. The quadratic form has certain isotropic subspaces. The isotropic subspaces have dimensions. You have a dimension 1, 2, 3, up to 6, or up to 7, depending on how you count things. And all these simplices have connection. For some of them are faces of some others. And altogether, these things for a complex of type D7 and that forms the building of type D7. And putting all these subcomplexes of type D7, you get the complex, the building of type E8 by putting the buildings of type D7 together. So that's how these things are built up. Now, if I want to describe a group of type E8, I give the following rule. I take a simplicial complex in which the vertices are numbered, some vertices of number 1, number 2, number 3, and so on. When I say are numbered, are labeled. There are many vertices of type 1, many vertices of type 2, and so on. So they are labeled. And I give you, as basic rule, if I take a vertex of type 1, if I take all the vertices that are linked with that one in the simplicial complex, I get another simplicial complex, which is a little bit smaller than the one I started with. And if this complex is a building of type E7, then the original one was of type E8. So this can be given as a definition of the groups of type E8 over the field of 2 elements. I say over any field. I take a simplicial complex in which the faces, in which the vertices are labeled with a number 1, 2, 3, 4, 5, 6, and so on. I give as a rule, I repeat, I give as a rule, if I take one vertex of type 1, for instance, I take all the vertices that are linked to that one, I get another simplicial complex, and the rule is that this form a building of type E7. A building of type E7, I already know what it is. I take a quadratic form in the space of 7 dimensions, and I take the isotropic subspaces, and this way I know what a simplicial, what a building of type D7 is. And I have this rule. A building of type E8 is a simplicial complex such that if I take any vertex of type something, so the rule will be this. I take a simplicial complex in which the vertices are labeled 1, 2, 3, 4, 5, 6, 7, 8. There are many simplices, many vertices of type 1, many vertices of type 2, and so on. If I take one vertex of type 1, and if I take all the vertices that are neighbors to that one, I get a building of type E7, which means a building corresponding to the picture that I get from this picture by erasing the vertex of type 1. So this is a way of defining locally the buildings of any one of these types. Actually, it does not work for G2 for some reasons that I can talk about, but it works for all the other types. And I can, in this way, you see that I have a sort of inductive definition of the buildings of any type. If I know already what is a building of type, say, A2, the next step that I know, by gluing these together, I know what is a building of type A3, and then the building of type A4, and so on. And I get the buildings of type E8. I do that over a field of two elements, for instance. I get a certain simplicial complex. It is a finite complex, and I consider the full group of automorphism of this building. And the group of automorphism of this building is the group of type E8 for the field of two elements. So I have, in this way, a geometric way to describe groups of type, say, E6, E7, E8, over any field, actually. It's an inductive way. I repeat the inductive rule. If I want to define a group, say, of type E6, it will be the automorphism group of a simplicial complex of type E6. The simplicial complex of type E6 is characterized by the fact that the neighbor, that for every vertex, the neighbors of this vertex form a complex for a building of type here. E5 or whatever you want to call it. So anyway, this is an inductive process to construct all these exceptional groups. Once you know the exceptional groups of all smaller types, the other ones are characterized by the fact that they are the automorphism groups of certain pictures, of certain simplicial complices, of which you know, in which you know the structure of the neighboring of the neighbors of any vertex. And so that's how I have described in geometric way all exceptional Lie groups. This description works not only for the exceptional Lie groups, but also for groups of higher dimension. The exceptional Lie groups are, well, when I say dimension, this method of constructing groups is quite general. You can construct groups with certain linking diagrams by imposing what the local structure is for every vertex. And I could in this way construct also groups, for instance, groups over groups over power series rings. If I want to construct a group of type E8, but not over a field, but over power series rings with one variable, I have to do this. As diagram, I take this, but I take one more vertex. I should have kept this. So I start with the E6 diagram, E8 diagram, but I add this, I add one vertex here. Then I get again a diagram, and I can play the same game. I consider buildings which have this diagram, and they are again defined inductively by the neighborhood of a vertex of type, say, 5 is a building which is a product of this and a product of and this. So I have here an inductive way to construct buildings of types which are not only of the standard types, but which are of a more complicated type. And this gives me, for instance, groups over power series rings with one variable. Well, I think I talked enough. What I told you here is not is the result only of rather complicated proofs. It's not immediate that group of type, say E9 here, is a group of type E8 over power series rings. It must be proved. The theory of groups over power series rings. I wanted to give you an idea. I'm sorry, I'm afraid I did not give much of an idea, but I want to give you an idea of how a group of type E8 looks like. You have a picture of the group with the Dynkin diagram. I mean, that's as I told you in beginning, that's all I know about a group of type E8. It's Dynkin diagram, and I have just this rule of construction. Hence this notion of building, because you have this construction. So the name of building was introduced by Bourbaki. I used a more complicated terminology, but the terminology introduced by Bourbaki is sort of suggested by this construction. Things are constructed like buildings, and the building blocks are the chambers. Excuse me for being so vague about this, but in my head these things are very clear.